So I'm just going to go through several examples. This book is pretty good with these examples. In chapter 11, 11.4, and these will be the types of equations I'll put on the test. That's where we are. I'll start with example 11.3. I introduced these last time, but I didn't really talk about them. You guys remember molarity from last semester? I know my class did it. Y'all, other classes did molarity too, right? Concentration. Right. There's also molality, and this is useful for some calculations that we'll do today. Or mole fraction, that's useful for some calculations we'll do today. Okay. So, example 11.3. The one thing these examples aren't good about is telling you what's the solvent and what's the solvent, what's the solute and what's the solvent. I'll do well to explain that to you when I give you questions on D2L, the practice, and on the test. I'll tell you what's the solvent and what's the solute. But in this case, this is the solvent. Water is usually the solvent if water is in a problem. Okay, so this is what's given. They tell you there's this many grams of ethylene glycol and there's this many grams of water. It says what's the mole fraction of each one and what's the molality of the solution. So that's what we're solving there. We have. Let me just do it like this. Of ethylene glycol. And we have 2,000 grams. So all I've done is just incorporate the power. So 2,000, and this is 3 significant figures based on the way it's written. This is 3 significant figures. Okay, so I'll just go ahead and do that, the conversion. So for mole fraction, we'll do this first, mole fraction. I need to know how many moles of ethylene glycol and how many moles of water. That's pretty simple calculation. Ethylene glycol is and water is H2O. So you already know how to do this. For H2O, the grams per mole is HO. There's 2 hydrogens and 1 oxygen. If you look on the periodic table, you get 1.01 here, 12.01 there. You add them up. So 16 for oxygen and 2.02 for water. And then we get O2. So you understand what I did here? Just found the molecular mass. And then for ethylene glycol, there's carbon, there's hydrogen, and there's oxygen. We've got 6 hydrogens, 2 carbons, and 2 oxygens. 12.01, 1.01. So you understand what I did there? Review from last semester. So now we can find the moles of each one of these. We got that many grams of ethylene glycol and 1 mole 62.08 grams. That's how we calculate how many moles we've got. If I'm being strict, this is 3 significant figures and that's 4. So I'm going to write this in 3 significant figures. Of that. And of course the water is 2,000 grams. This was 3 significant figures. This is really 3 significant figures. $2,000 divided by 18.02. That's what my calculator says. If I'm keeping 3 significant figures, I'm keeping these 3. The 9 rounds to 0, so really what I've got is so when you're doing mole fraction, you just find out how many moles there are of each thing. And then the total moles goes on the bottom, and the moles of whichever component you're calculating goes on top. Total number of moles is 35.8 ethylene glycol. It seems like I should be able to do that in my head very easily, but I'm not going to. 35.8 plus. Total moles. And then the moles, okay, so the mole fraction, fraction of ethylene glycol is 35.8 over the total moles, which is 146. The mole fraction of water is 111 over 146.
Would it be 147?
Where's that?
36 plus 11. Not a big deal.
Yeah, but I want to do it right, and I do make these mistakes, so plus 111, yes. Thank you. 47. 47. 47. So it's that simple. Mole fraction, 35.8. 3 significant figures, so I'm going to go 0.244. I rounded that last digit. And these should add together to be very close to 1.244 plus 7.8. Wait, that's right. This is 0.755. 0.244 plus 0.755, 0.9999. So this is the mole fraction for these. .95 and .92. Why did they take two significant figures? .244. Well, we just did one of the more fractions. Sorry. But I got this. Mole fraction, and then molality. Molality for this. So now we're doing the moles of the solute and kilograms of the solvent.
Are we on 11.4 now?
Yeah. Yeah, 11.4. These are the examples I think you solved the other day in class when I said I was going to do them, and then I did. 1.3 molality. So we need the kilograms of the water. We're going to keep the moles of the ethylene glycol. What am I doing? Okay, so we have this, and that is right? It's just 2 kilograms of water. If it's 2.00 times 10 to the 3 grams, then it's 2 kilograms. You with me? Kilograms of solid. So kilograms of water. So that would be the answer to this one. So I will put problems like this on the test. For now, just look at example 11.3 for practice. There's also a check your learning one. You can do one yourself. But I'm working on getting some of these in D2L so you have more than 2 examples to practice. So now I'll do 11.4. Example 11.4. This one just wants mole fraction of solvent and solutes. And it gives you one fact. Little m as in molality. And here's an example where it's not clear, but I would tell you this if it were a test or a question. But they don't say that explicitly. Okay, so if this is true, so this is a very summary way to write this, but that's the more explicit way to write it. 3 moles of NaCl and 1 kilogram of water. If you want to know the mole fraction, you already have the moles of NaCl, and they don't tell you 1 kilogram of water. So we're going to use the molecular weight of water again. One kilogram of H2O is 1,000 grams of H2O. And then grams of H2O. Does that make sense? Convert to grams, and then we'll use the grams per mole, and now we can find out how many moles of H2O we have. And ultimately, it's 1,000 divided by 18.02. We've got 2 significant figures, so it's just this 55. All right, so the mole fractions are 3.0 moles of NaCl. And we have to add these together, so 3 moles of that. So our total moles is 55 moles of water and 3 moles of NaCl, so 58 total. And I would call this X NaCl. 3 divided by 58. 2 significant figures will give us 2. And the mole fraction of water is 55 moles of H2O over 55 divided by 58, 2 significant figures, 0.95. And those add up to about 1. Rounded. Makes sense. Simple, right? And we are pretty far south, but how many of y'all think it's going to snow? 1, 2, 3,
If you
4,
look
5.
at it in the current.
I really didn't think we were going to get hit by ice and stuff last weekend, and we didn't. And my gut tells me it'll snow overnight, but it'll melt before we wake up. It would be fun, but all right. So this problem tells us 11.5 says you have 0.556 molar, so that's from last semester, the molar glucose. Glucose solution. And here water is the solvent. It really needs to be stated. This book just kind of belies that. It also tells us the solution density, the solution, that's the solvent and the solute together, is 1.04. So that's the information given. It wants to know the molality. What is the molality of the glucose solution? This means it's moles of glucose in 1 liter of solution. It's not 1 liter of water, it's 1 liter of the glucose solution. So if you want molality, we're going to need the kilograms So we got to get to the kilograms of water. We can do that, but first we're going to find out how many kilograms of solution. So we're going to go, if we have 1 liter of the solution, and I guess I have to go to 1,000 milliliters is 1 liter. And now I've got 1.04 grams per milliliter. And then we end in grams. I want to end in kilograms though. Since we're trying to get to kilograms, we'll go ahead and do this. Okay. That'll tell us how many kilograms of the solution. And it's basically,
Wait, is the thousands of milliliters supposed to be on the top so it cancels?
yes. I knew I was going to stumble around if I don't go over this stuff before class. I show up brain dead. Okay. Liters cancels, milliliters cancel, grams cancels. There, that looks good. So the thousands just cancel each other, so let's just write that. Kilograms of solution. Right. The solution is made up of both the glucose and the water. So if we subtract off the weight that comes from the glucose, then we actually have the kilograms of only the solvent. I'll write it like this. Kilograms of solution equals water plus some number of kilograms of glucose. Another thing this book is kind of bad at is telling you where the grams per mole come from. Glucose is a huge molecule. And I will tell you, I'll either give you the formula for the molecule or just give you the grams per mole. In this case, they don't say it until they use it later, but that's the molecular mass of glucose. So you need that to figure this out. All right, to figure out the grams of glucose, the kilograms of water is 1.04 kilograms of solution minus, we subtract from both sides the kilograms of glucose. less. Alright, so kilograms of glucose then, if we have 0.556 moles of glucose, and 1 mole of glucose, grams of glucose, moles cancel. Okay, so 182 times 0.556. 3 significant figures, 4, so I'm going to keep 3 here. It's, my calculator says, but I'm going to keep 100. Oh, I guess I need that in kilograms. Got it. .94, and I guess I have 3 significant figures, right? So now it's just moles of glucose over kilograms of water. And that should give us the answer. 556 divided by 0.940. I get 0.591. This should be 3 significant figures, right? Sorry. Yeah, this code, man. Is it the subtraction? We have 3 here. It should be 30 anyway. The book says 0.59. It should be 0.59. To finish it out, you put M. That's the molality solution. So you were given the solution in molarity. We had to go through that walk to get molality. Oh, that's 11.5. Okay. So now we do things with these new concentrations. And I'll put it here. Solution. Mole fraction of the solvent. That's the vapor pressure of the pure solvent, and this is the vapor pressure of the solution. Thanks, solvent. So, if you can look up the vapor pressure of a particular solvent, once you put that in solution, you can find the vapor pressure of the solution. So in this case, (92.1) glycerin, and getting that. Grams of ethanol is it tells you pure vapor pressure star atmosphere, and it wants you to solve for the vapor pressure of the solution. So all we really need is we're going to multiply this by the mole fraction of the solvent. The solvent here is glycerine. Okay, so we need the mole fraction of the solvent, which is ethanol. So you have to calculate this. How many hydrogens are in this formula? What is it?
6.
You're tempted to think 5, but this is just a different way of writing these formulas because the OH go together, and chemists like to see it because it means something. So there's actually 6 here, so don't miss that. 12.01, 4.02, 6.06, 16. 8. Did I do that right? 46.08 grams per mole. Okay. So if that's true, the moles of ethanol, we have 184 grams of ethanol. We also need the moles of glycerine, which is C2. H. How many H's are in this formula? That formula is telling you. I guess the way it's written is like this.
92H5.
I must have written that down wrong.
That's three.
I wrote it down. C3. Good Lord. I told you I'd stumble around today. I'm not as prepared. C3H5OH3. C3H5OH3. C3. Okay, so how many hydrogens? How many hydrogens? Huh?
8 is 8.
It's smaller. So the molar mass of the glycol, the glycerin, is C3H8O3. I'll use the calculator. 12.01 times 3. What's 3 times 16?
48.
Is that right? 92.11? If I add them up. Did I do that right? So the number of moles of glycerin, which is one mole of glycerin is 92.11 grams. I guess that's 1 mole. Ninety-two point one divided by 92.11. 0.1. We're in 3 significant figures, and my calculator says 9998. If we're keeping 3, it rounds up to exactly 1. Four moles of ethanol, 1 mole of glycerin. So for the pure solvent, the solvent here is the ethanol. So pure ethanol in our fraction is 1/4. Oh, yeah, I didn't do the mole fraction, right? The mole fraction. Ethanol, there's 4 moles of ethanol. So it's 5 on the bottom and 4 on the top. What's 4 divided by 5?
180.
Better question, where's my time? What did you say?
180.
That. So if you dissolve this much glycerine and this much ethanol, the vapor pressure of ethanol will change from this to this, go down a little bit.
So that's the pressure that's
This is the vapor pressure,
of the solution.
pure solvent vapor pressure, and this is the that's the new vapor pressure of the solution.
And so that's what that 0.1, 0.2 is.
Yeah, that's the new vapor pressure. If you have pure ethanol, this will be the vapor pressure above the solution. If you put this much glycerin in it, this will be its new vapor pressure. So any of these I'm going over, you should try to check your learning thing. Just for practice. I am in the process of getting some of these put up on D2L, so you'll have more examples. It'll look just like the test. I'm going to seven. Okay, so the generality here is if it lowers the vapor pressure, so you've got your pure substance, and then you have your not pure substance, it's got a little bit of solute dissolved in it. Necessarily, the vapor pressure goes down a little bit when you do that. So what do you think that does to the boiling temperature? It's the opposite. So let's call this temperature, and let's say this is let's call that the boiling point. All right, you remember that the vapor pressure equals the pressure over the solution at the boiling point. If you bring down the vapor pressure a little bit, then you've got to work harder to get to a boiling point. I can explain that a little bit better, but I just want to go through these calculations today. The point is, boiling point of the pure substance should we call it the not pure boiling point. Plus a little. So it increases the boiling point. I'll just write it like this. And then those two generalities are always true. If you have a pure substance, so then let's say liquid, pure liquid, and you put anything in it, anything that dissolves in it, doesn't matter what it is, whether it's an ionic compound, a covalent compound, whatever. If you put it in there, you're going to have to put it to a slightly higher temperature to make it boil, and a slightly lower temperature to make it freeze. Does that make sense? That's the generality. And it doesn't matter the identity of the stuff you put in there. Had bacon and sausage for breakfast, it made me thirsty. Okay, so I guess I'll show you this. I do have a PowerPoint. This is in the book. I have a PowerPoint that just shows these examples I'm going through. But I need this chart. So it's this chart I'm looking at. But this book is not really about telling you, again, information you need to know. So this is 11.7. I would rephrase this as, assume ideal solution. Ideal solutions are basically really, really dilute solutions. You only have a tiny amount of solute in the solvent. If it's...
You want to turn it down? Sorry, thank you.
No, it's fine. Tell me if these fail. We've been struggling with technical difficulties in this room ever since we started doing it. That's all I'm going to do is jiggle that. Okay, so jiggle that one. You call that T last semester. I became this group with it. So these constants, boiling point elevation, freezing point depression, constant. So 11.7 is the way it's phrased. Assuming ideal solution behavior, what is the boiling point of 0.33 molar solution? So all you're told is, and since it doesn't matter the identity, this is telling you 0.33 and these constants are KB, and I'm going to give you specifically. I would give you this in a problem, but they use here 2.53. So if you look at slide number 6 for today, and you see where it says benzene, and the KB is 2.53, it's 2.53 for any non-volatile solid. But I would give you in a problem. Degrees. Degree C, not per mole, per m. So 0.33 m is what we've got here. So a 0.33 m molal solution, and this is the Kp. So the way you calculate this is 0.3 m, 2.53 degrees C for 1 molal. You multiply those together. .33 times 2.53. So now, does this one tell you the pure? Yeah, there's problems with it. 80.1. Did I just cut something off? Yeah. So we're assuming this is benzene, I guess. But it doesn't tell you 80.1. You would need to know that to solve this. So assume you're given this, and you're given because you would need to be given that. I'm not expecting you to memorize the boiling points of every solvent in the world. But basically, you just add that 0.830. It rounds up to 81. We did the significant figures wrong. 0.33 times 2.5. So that's two significant figures. So that has to be 2. Oh no, it is 1 after the decimal. I'm wrong. Let me get my significant figures correctly. That's the new boiling temperature. honestly, I just took a lot longer to describe something that was way more simple than it was. But you need the constant. You need to be given the constant. I'm not expecting you to memorize the constants. Okay, this one, 11.8, actually gives you the proper amount of information. So I should probably just take. Let's see what it is. For the non-volatile, I would just give you the 2.53 kV. I think that's the one they're going to use. All right, so the information you're given. Of 92.1 grams of iodine. That's I2. And what's the new boiling point of this solution? You also need the boiling point of iodine, and they don't give you that. I guess they expect you to look. I gave you guys the other day. Which one it is? But when I make these questions, I'm going to give you this information so you don't have to go dig it up somewhere. Come on, PowerPoint. All right, I'm just going to. $61.15. So you're given this, and I would also give you this, so you're not having to look stuff up. Degree C. write this as kilograms. So to look up iodine on the periodic table. You'll have this particular periodic table. Iodine is 126.90. So that you would look up, and you got 92.1 grams of I2. There's our moles of I2. So next we want chloroform. So that's going to give us the 0.363 divided by 8. Lowercase m. And now we can use Sorry. I will give you that and a problem, so you know what it is. So now we got to multiply 0.454. So now that we have the m, we'll go 0.454 m times 3.63 degrees C over 1 m. That's this. And you get 1.65 degrees C. So now you're going to take the boiling point and add 1.65 to it, and that's the new boiling point. Does that make sense? And the new boiling point is I think we have to report 80. Two significant figures. That was two significant figures. I mean, three. That's three significant figures. That's 4. So when we found m, it was 3. And this is given in 3, so that's 3. So 62.8. It gives you the normal boiling point of 61.26. So I looked this up on Wikipedia, and they gave 1.5, but if it's 2.6, Again, I'm just gonna give you that as a problem, so you're not hunting for things. So that's what you, as long as you understand the process. Okay, we'll do a deep freezing point depression. But it's really just the same process. Okay. Again, .9 gives us 0.23. They don't tell you that the solution is water, but I would tell you in a problem. I would tell you all of that. You can't, just because something is a solution, you can't assume that the solvent is water. I might be regretting using OpenStack a little bit, but it was simple, right? You didn't have to go buy a book, you didn't have to spend any money. So we're going to use this for benzene. Benzene's freezing point is 5.5. Water's freezing point is 0. We want the 1.86. Water. So I'll give you that in the problem. And I suppose I'll give you this too. Boiling point normal for water. Probably already know that. Water freezes at 0 degrees C, boils at 100 degrees C. All right. Is that what I put? They use 0.5, 0.12. They use the boiling point. Okay. This is why I need to go to these estimates. Let's just leave it there. I will look at these more closely before we meet next time. So maybe OpenStack sucks worse than I thought it did. But I'll just stop there. Because I need to look at these a little closer.